I got this sample value and I want to compare it to this, or compare the proportion to this. How bad am I? I mean, it's not going to be exact. So how bad is bad? And the view graphs will do it right away. It gives you a nice little example, and maybe I'll just work through it because it kind of helps. But so we're going to come up with a statistical approach to take these sample values we've got, whether it's a mean or a sample proportion, and assess it relative to what we think it should be, and come up with a statistical way to say, yeah, this is bad, or no, this is good, and be able to quantify it in terms of a confidence level, a percentage, if you will. And so we're just going to apply these. Either you can do a confidence interval, but we probably won't do that. You can also compare it to a critical value. We will do that. Or you can calculate a probability. So there's the three ways to look at it. Each way leads to the same decision. It's just how do you want to explain it. So let's look at this first little example that they'll teach you how, or they'll set this context again. So let's see. Yeah, so we're going to learn the basic principles, which means we're going to learn how to state a null hypothesis and an alternative hypothesis. You probably hear that all the time. If you've read a psychology paper, I mean, read one psychology paper and it'll talk about that. Oh, the null hypothesis is this. That's always the little H0. So we'll learn about that. We'll learn that vocabulary. That's nice. And then we'll be able to apply it to a mean or a proportion, and you know how that is. That's either whether we took an average of a mean of a bunch of numerical data, or whether we had categorical data. The assumptions behind each of the methods, this is just going to be whether you knew standard deviation or not, that sort of assumption again. And then, yeah, the ethics and some of the problems. So let's start getting into this and let me make sure this is going to do it. Yeah. Let me see. Yeah, okay, yeah, it does. I thought that's the way they went. They just are starting slower. Okay, yeah. So you know, your hypothesis that you're going to test is a statement about the population parameter, right? Because you know the population parameter is what you care about, but the sample thing is what you take. So the population is your manufacturing process going on. The sample is your sample of cereal boxes or light bulbs or whatever it is. It's the finite amount, not the whole thing. So, for example, you would think that the population in a city, their average cell phone bill is $42. So, or a proportion, you might say, hey, the proportion of people that in the town that own cell phones is 68%. So you notice, as they've done before, if you want to be consistent, their notation, you know, an average on a population is not an X bar, but it's a mu, and the proportion on a population is a pi. So we're gonna state our hypothesis about a population parameter, if you will, whether it's the mean or the proportion, but we're going to make our calculations based on something from a sample. So your null hypothesis is what you're trying to test. So for example, you've got a manufacturing process making bolts. And so your null hypothesis would be, hey, is the mean diameter of the bolt 30 millimeters? So mathematically, the way that's always written, the way you'll see it in papers is the null hypothesis, null is 0, H is hypothesis, and you're saying, hey, is the mean diameter 30 millimeters? And so your null, when you state a null hypothesis, you're trying to be pedantically correct and and be able to talk with good statistics folks. You're always stating your null hypothesis relative to a population thing, population parameter, not relative to a sample. So remember, the mu is the population mean, the whole mean of the entire group, and the X bar was the average or the mean of the sample you took. You know, 15 light bulbs we measured, or 20 volts that we measured, or however many. All right, so that's one rule with the hypothesis. And you begin with the assumption that it's true, and then you take your samples and then try to show that there's reason to believe it's not true or not. And so you're not you may or may not show that it's not true. You know what I mean? We're going to take a sample, we're going to compare this mean that we get from this sample to the population mean that we think we have, and we're going to compare it statistically using our confidence intervals or our critical values, and we're going to say, well, was it likely that we got this mean or not? And that's going to be how we make our decision. And you'll see that in a minute. So the null hypothesis is always going to have an equal, or perhaps you might have a less than or equal or a greater than or equal, but it's always going to have an equal in it. Because like the previous example, we're asking, is the mean bolt diameter equal to 30? When do we have these? Well, in situations where you don't care about one side or the other, right? If in the case of the bolt, we don't like it to be less than 30 or greater than 30, but one of the examples they give in the book is like drive-through service times. We just don't want it to be greater than some number. And we like it. We don't care if it's 0 drive-through service time. That's great. So we're only looking at one side, or maybe we've got a manufacturing process. We want our holes to be a certain size or larger so we can fit something in. So we're going to just pick one side or the other, and that's the only difference between that is. Then the alternative hypothesis is, the other side of it. So in the bolt example, if we said, hey, we're wondering if the mean diameter of the bolt is 30 millimeters, and that's our H0, then our alternative hypothesis, which is H1, is, well, it's not 30, okay? Or if we're worried about something being, greater than or equal to, then the alternative hypothesis is, well, it's less than. It's just the null, the negative of what you just stated. So, conceptually it's not hard. We're going to ask a question about our process, and the null hypothesis is, what we think it is now, and the alternative is the opposite of that. And you may or may not prove that, and it's generally what you're trying to come up with. So for example, in the bolt question, our H0 is our mean diameter 30 millimeters? Well, we're going to take a sample and it's not going to be 30. And so we're going to ask the question, the alternative hypothesis is, well, is it not 30? And that's what we are kind of trying to show. Because if we show that it's not 30, then we've got to do something. Well, we know it's not going to be 30. I don't mean that. We know it's not going to be 30 when you take a sample. Obviously, it's not going to be exactly 30. But we're trying to show, well, did this diameter that we got from this sample, is it bad enough that this makes us believe that we're sampling from a population that's not 30? That's how you got to think about it. Because it won't be exact, never is, because you're taking a sample, but is it so bad that this causes us to believe our process is not doing what we think it is? So let's discuss that in the context of an example. So, we got a population, and we think that the average age of this population is 50. So our null hypothesis is, hey, the mean age, the mean age of the population is 50. Our alternative is that it's not. Okay, well, let's sample it. So we got all these people, we take a sample that's a smaller number than the whole people, and we come out with, we came out with a sample average of 20. Well, none of us in this room, given that sample, would think that the mean population age was 50, unless we had some reason to believe we really goofed up our sample, right? I mean, maybe if we had a whole town and went to the kindergarten and took our sample from there, we'd understand that, okay, that was dumb, that was bad. But assuming that we've made a reasonable sample, reasonable size sample, and if we came up with the mean age in the sample, and notice they're using X bar, was 20, and our hypothesis was that this population had a mean age of 50, we'd all say, well, that's stupid. It's not. That's wrong. Something's wrong with the population. Our ideas are wrong. Our process isn't working or whatever. The probability of getting that is very small, right? We know how that probability curve goes, and there is a probability that if we had a population with a mean age of 50, that, hey, we could take a sample and maybe we'd get 20, but the probability is so darn small, 0.00001, that it's just so unlikely that anybody with any sense who's working on a process that has that is going to say, I need to take some action. Okay, so in other words, getting samples of 20 is so unlikely. If the mean of the population truly was 50, you conclude that that's not right. And so graphically, it kind of looks like this. if you think that you've got a normal distribution that has a population of 50, then it's really unlikely, way down here, that you did a sample and you got a mean of 20. It's also unlikely on this side too. So since it fell way down there in the tail, either down in this little tail, or if it happened to be up here, we'd have gotten a mean age of 100, then you say, no, I've got to reject this null hypothesis. Something's wrong with what I'm thinking. I got to do something. So your thought process is, hey, if that sample mean is close to the population mean, then you're going to keep the null hypothesis most likely. Because if we got 51, we think, well, yeah, that's right. Or 49, we think, yeah, we probably did have an age of 50. But if it's far away, like 20 to 50, okay, we're going to reject it. But now, well, what if it's 45? Or 55, or something. How far is far enough? How bad is bad enough? Yeah.
So in the previous example, if you did get that it came out to be 20, but you still think that, like, hey, I think 50 is correct, and then would you just go out and do another sample?
Yes, I would. Yes, or I would go and say, what is unusual about this sample that maybe I could conclude I got 20, like I said, because you went to the kindergarten sample, or did something where all the old people were gone because there was an old people gathering out of town or something,
So just use common sense to either take another sample
or try to figure out why you could reject this, right? But you're right. And if you took another sample and you got 20, like golly, goodness, my null hypothesis is definitely wrong. Yeah, and so what we're going to try to do with our whole approach now is to try to quantify this decision making, so that when you get 45 instead of 20, I can make a statement about my belief or non-belief in the null hypothesis in a statistical way. I'm 95% confident that this hypothesis is okay. That still doesn't mean it's correct. You still could goof up, but at least you've stated it in a statistical way, and people can hopefully understand it. Hopefully. So here's what we're doing. Think about our little t distribution or our z distribution. If it fell in here close to the mean, we're happy with it. And when we get a sample mean that falls way out here, we're not happy with it. And so here's the region we're going to keep our null hypothesis. When our sample mean sits right next to the real mean, yeah, we like it. When our sample mean is way out here, we don't like it. Well, what's way out here? Well, remember, we've come up with a way to decide way out here. We'll put 5% and 5%. We'll put 2.5% and 2.5%. And we've got these tables that tell us what this value is when we put 5% and 5%, or 2.5 and 2.5, or 0.005 and 0.05. We've got these critical values, and we've got these distributions, either with a z distribution when we know what our standard deviation is, or that whole big family of t distributions when we didn't know what the standard deviation is. And so, okay, we've got our approach now. Now we can just use those things, the things we learned last chapter, to state these hypotheses, take a sample, compare our sample to what we hypothesize, what we think the population should be. And if it falls out here, right, no, we're wrong, we're not thinking right. If it falls in here, yeah, we're okay. And so that's the whole approach in this chapter. So it's not conceptually, it's got a little twist to it because we're asking this question, but mathematically and the tools we've already learned, we've already got all those things. So let's talk just a little more about it, because there's a few terms that statisticians use, and you'll hear this. And so I think it's important to know what these are. You probably heard them before in other contexts. So there's two types of errors. There's a type 1 error. That's the type of error when you reject a null hypothesis that is true, but you shouldn't reject it. That's that's kind of what you're asking. You took a sample, you got 20, and it really was 50. It just was a goofy sample for some reason. Really strange sample, and that does happen, right? Because why does it happen? Because there is a finite probability that you get those goofy samples. You expressed it. I'm 95% confident I'm in here. That means 5% of the time there's some goofy samples. Hey, if you don't like that, well, say, okay, I'm bump it up. I'm 99% confident I'm in here. I got 05, 005, and 005 out here. Okay, but that's going to cost you more samples and things like that. All right, and then there's the type 2 error, which is when you have it is wrong. Your null hypothesis is wrong, but you don't reject it because of your goofiness of your sample too. We'll look at the end. There's a topic that kind of shows you where that is graphically. So you may have seen it expressed this way. A lot of statisticians and researchers put it this way, where if the hypothesis is true and you don't reject it, oh, that's good. Right? That's what we wanted to do, right? Or if your hypothesis is false and you do reject it, that's good. That's what we wanted to do. And here's your type 1 error when it was true and you did reject it. And here's your type 2 error when it was false and you did not reject it. These two, beta we haven't shown graphically. Again, we'll do that at the end. And it's not the clearest thing. I think you have to think about it. This we've shown, right? Remember that the alpha is what you pick. You pick that. The alpha is those probabilities that are in those two tiny little tails. And so, right, the probability that the hypothesis is true when you don't reject it is 1 minus alpha, right? It's all that big glob in the middle, of our nice little distribution. Remember, here it is, and you put alpha over 2 over here, and we put alpha over 2 over here. So, well, all this is 1 minus alpha because the area under there has to be 1. And so here's when H0 is true, and when you sample in there and it falls in there, that's when you say it's true. So there's 1 minus alpha probability that your test is going to come out correct. You're going to make the correct decision. But there is an alpha probability that you're going to goof up, right? And that's what it means to say that I'm 95% confident that this is true. There's a 5% chance I goofed up. Well, this is statistics, right? We're taking a sample. The only way to be 100% sure is to, measure the whole population. And that's the whole point of this class. We can't do that. We can't afford that. No one can afford that. We got to take samples. So let's take some samples, make the best decision we can, recognizing that, yeah, we can make mistakes. And if the cost of those mistakes are high, then, lower this, right? Don't put 5% here, put 1%. Just keep pushing. And somewhere, like everything in engineering, it's a trade-off between how much can we spend on samples and how much can we afford an error. Maybe the error is not that costly. That's fine. We put 10% in there. So they've got words. They've got names for these. We've already talked about that one. They've got names for those. That's sort of vernacular. That's what's next. They call that the confidence coefficient. Of course, the confidence level we've already mentioned. The power, there's the word. The power is 1 minus beta. It's the probability of rejecting it when you should have. Okay, and again, the little section at the end will show that graphically, what area that is. And again, it takes a little bit of study and a little bit of thinking. So if, you can only get a type 1 error if H0 is true, right? Remember where it was in the box? The type 1 error was not rejecting or rejecting H0 when it was true. Well, you can't have that if H0 wasn't true. And same conversely with the type 2 error. You're not going to get a type 2 error if H0 is not false. That was only in that right column. And if you increase alpha, if you increase your rejection area over there, you have a greater chance of making the type 1 error. Then you'll have a lesser chance of making the type 2 error, and that's not intuitive. You'll have to either accept it, or we'll have to look at the graphical thing at the end, and then you may understand it. And so vice versa. Obviously, you see, the converse is true. Then if beta goes up, that meant that beta goes up when the difference in between them is close, right? And when beta goes up, alpha goes down, just like the other side. When beta goes up when your standard deviation goes up, and beta goes up when the n goes down. Let's see, are those intuitive? So your beta your beta, if you remember, was, let's see, if we look at our little box. Yeah. Beta was the probability that it was false and you didn't reject it, right? Okay, so intuitively you could say to yourself, well, yeah, if I had a big standard deviation and I had a false hypothesis, but I have a big standard deviation, I might come back, you know, I might get it's easier for me to get a sample close to what I think it should be, and so I wouldn't reject it, I'd make a type 2 error. So these things, you know, again, I think these things aren't intuitive. And I think it takes a little thinking about, oh, what am I doing? How could that affect it? I mean, this one I think you might be able to see, like I said. And we'll try when we get to that last little, they call it the online section, where it's drawing the pictures of two distributions and trying to show you where these errors are relative to here. Maybe it'll help the intuitive thoughts about it. It doesn't matter really. It still doesn't affect how you use it. You know, these are just discussions on it. All right, so let's see. So yeah, so again, back to where we were. So we had the bolt problem, and we were asking ourselves, was the mean diameter of the bolts in our population of all the bolts that we're spitting out of our factory 30 millimeters? So that was our null hypothesis. So our alternative is no, it's not. And we're going to ask it at some alpha percent, right? Which means we're going to put alpha over 2 over here, alpha over 2 over here. We had these critical values. Okay, and this is where we say we are wrong, our null hypothesis is correct. This is where we say it's correct. And this is called a two-tailed test, right? Why is it a two-tailed test? There's one tail here, one tail there. Why is it a two-tailed test? Real simple, because we asked if the mean was equal. That means we don't like it when it's less, and we don't like it when it's more. So we got some, you know, I don't likes it over here and I don't likes it over there areas, right? You can move either direction, okay? As opposed to, hey, what's going to come later in a few more view graphs is a one-tailed test, right? Because that's the one where you got a greater than or equal to or a less than or equal to, because we are not going to care if it falls over here if it's less than, or we don't care if it falls over here if it's greater than. And so the only difference between the one-tail and the two-tailed test is if I talk about 5% confidence level. In a two-tailed test, remember I put 2.5 over here and 2.5 over there. If I talk about 5% in a one-tailed test, well, I put all 5% on one side. That's the only difference. So your critical value will be different, right? But just remember that. And that's 10%, you know, here I put 5 and 5, 10% in a one-tailed test, I cram it all on one side. That's the only difference. So yeah, the critical values are different. Because I said, you know, one, I'm got 5% here, the other I might have 10, but your statement is what you're dealing with. What do you care about? How do you state it? Okay, so here we're dealing with numerical values. We've got a mean of a numerical population, not a categorical data. And remember before we had two situations, one where we knew the standard deviation and one where we did not. And so remember when we knew it, we had the z-test when we were doing we were using z for our confidence intervals. And when we don't know it, we use the t-distribution. And remember why, when you knew it, you could use the z-distribution looked like that, and the t's got fatter and shorter, and the t's were just like a z, except basically had more uncertainty because, yeah, you have more uncertainty because you don't know this, all right? And so that's the difference. You use this one when you know the standard deviation, this one when you don't, and you use the sample standard deviation. And again, remember, this is kind of the unlikely situation. Maybe you know it because you know it from the past, or you got the physics down, you know it should be this or something, but this is the more likely situation. But we'll explore them both because the procedure and process is the same. So, hey, what are we going to do? Well, gee, we're going to come up with our z measure of what we came out of our sample, right? So x bar is our sample mean, and mu is what we thought it should have been. Here's our known standard deviation. Here's our square root of n. Remember, n is the number of samples we took. This is the same old z-stat we've used for 2 chapters now. And we're just measuring, you know, how far away are we from here in a normalized way, right? It's always normalized. That's what this is doing. You know, and that, remember it had that name, standard error of the mean. That's all we're doing. Okay, and then, yeah, let's see. So we convert X bar to Z stat. We determine those critical values, and the critical values are related to what we thought, right? We want 5%, 2.5%, 1% over in that tail. So we come up with those critical values. We're the one that decides that. And then if the test statistic, you know, falls out past the critical value, like over here, oh, well, gee, that's unlikely. It shouldn't have done that. It was a low percentage that it gets out here, then we reject the null hypothesis. Otherwise, you know, if it falls in here like the first time I drew it, or it falls over here, oh, okay, we'll keep it. Real simple, real simple. And so now we've come up with a way to describe how far is too far. Right, this is too far, right? This is too far. Because this is the case where it's equal. We can have two too fars, right? One on one side, one on the other. If not equal, one side less than the other. So let's see. Yeah, well, in fact, they drew this for us. I should have drawn it over there. So there are two cutoff values defined in the region rejection, right? Yeah. So this is your from your table or from your inverse function in your Excel. Okay, based on how much you want to stick out there. Yeah. So mathematically, this is how you draw it. Yeah, look, we got the null hypothesis, the alternative hypothesis. And believe me, you read the papers where people are real statisticians. They'll write it right there. There'll be equation 2, in the paper. It'll have that in there. It'll have H0, it'll have H1, and you'll know what they're talking about now. So what's the process we do if we were faced with this problem? Let's take the process in words. Well, hey, you come up with a null hypothesis. The mean diameter of the bolts is 30. Okay. Well, then that immediately tells you what the alternative hypothesis is. The mean diameter of the bolt is not 30. Okay. And then you choose your level of significance, right? I want to be 95% confident. I want to be 90% confident. I want to be 75% confident. You can remember the table went down that low. Okay, you pick that, then you get your Z-stat or your T-stat. I guess I should only say get your Z-stat because right now we're talking about the known sigma case. So you calculate your Z-stat from what you got, the mean from your sample, X bar, and your standard deviation that's known, and then get the critical values from alpha, and find out where the reject and non-reject region is, and kick out the null hypothesis or not. Value test statistic, and make the decision. And then here's what you want to say. If it falls in the non-reject region, you do not reject it. Okay, that's a good. I like that. I'm glad they told us that. If it falls into the rejection region, reject it. Okay, and express the conclusion in the context of the problem, which the conclusion is going to look something like this. Let's see. So they'll put there. Wait a minute. Let's see. They say it. That's 2 more view graphs, right? Let's see. Golly, it's 4 more view graphs. All right, we'll go through the stat. But the important thing is when you come to the conclusion, you don't, when you state the conclusion, I thought that's what they were going to show on the next view graph, you don't say, well, we've just now proven H0 is true. You just state something like, well, there's not enough evidence from this test to show that it's not false. Because you're really not, it's a sample, it's a statistic, you're really not proving it's true. So let's see. So let's go through it. So let's go through an example. To test the claim that the mean diameter of this bolt is 30 millimeters, and assume that we know the standard deviation for some reason because we know this process, it's going to be 0.8. So let's do the null hypothesis like we said. Mu is 30. The alternative is, well, mu is not 30. This is going to be a two-tailed test because it's got an equal in there and equal only, no greater thans or less thans. And remember our little discussion about 10 view graphs ago, the null always had an equal in it, either equal or less than equal or greater than equal to, and the alternative never had one in it, so you know how to state this properly. Specify the desired level of significance. We're going to do 5%. So we're going to have 95% confidence. We're putting 2.5% in each of the tables. We're going to take 100 samples, okay? And because this is known, because our sigma is known, yeah, It's a z-test. Because we don't need to have the t-distributions that give us some wiggle room. We use the nice tight z-one. So sigma's assumed, so this is z-test, well they already said that, thank you. Alpha is 0.5, so the critical values are plus or minus 1.96. You probably got that memorized by now. Probably. And if not, we can look in the table and see. In fact, I'll probably just show it to you. Yeah, we'll look at it when I'm going to pull up the T one and look at it. Yeah, so you know where it is. You go on the table at 0.025. All right, and collect data and get this test statistic. So hey, we took a sample of 100, the mean, and we got 29.84. So, you know, in our previous discussion, is 29.84 good or not? You know, it's not 30. It's never going to be unless we take every vote in the population. And so, yeah, it's 0.16 off. Well, I don't know if that's good or not. In the past, if we don't have a way to state, that's good. You know, in high school, you're going to say, well, that was good. It's close to 30. I'm happy. You might have done a percent error or something, right? You take 0.16 divided by 30, and you say, okay, that's good. Low percent error. I'm happy. Okay, but this is a better approach. So let's get our z statistic. Normalized distance away. Okay, -2. Well, you know, -2 is a lot. It's really compared to that. Yeah, yeah. So let's draw our little picture, right? So here's where it fell, right? Here was our critical values. Because we put 0.025 over here and put 0.025 over here. Why'd we do that? Because we wanted to, right? We're the ones that said that. And our z statistic was -2. It's less than -1.96. It's over here in the rejection region. So that says that even though, you know, 29, or was it 29.86? That what it was, or 28? Yeah, 29.84 looked pretty darn close to 30. But for a sample of 100, with a standard deviation of 0.8, that's not so darn close. It's not within 95% close, is it? So it's in the rejection region. So hey, our conclusion is let's reject it. All right, reach a conclusion. So since the z-stat fell over here, we reject the null hypothesis and conclude that there is significant or sufficient evidence that the mean diameter of the bolts is not equal to 30. You know, again, it's not 100% sure that was the case. We might have got the goofiest sample, you know, but it's far enough away that if you're the person running the bolt factory, it warrants you to go do something. What do I mean to do something? Well, if do something's going out and turn a dial and it doesn't cost you but 39 cents, well, go turn the dial. If do something is going to cost you $1 million because you're going to shut the factory down for 2 weeks and debug a process, maybe you might want to take another sample, right? Do something means go act, but your actions may be different depending on the cost of what your actions are. And so, but for right now, with that sample and that hypothesis, we think something's wrong with our process because it just really was unlikely that we got out there. Still could have happened, but it's unlikely. All right, so now, that's one way to look at it, right? We compare a z-stat -2 to a z-critical -1.96. Some people don't like that. I like it, it's clear as day to me. But maybe you might, instead of expressing it that way, would like to express a probability of falling out there in that table. Because maybe some people understand probabilities better than they would the comparison of two numbers. And I could see why. You know, if I come in and tell you, well, look, my z-stat was -2 compared to -1.96, if you hadn't had statistics, you'd be like, so that's close. 2 is close to 1.96. So maybe instead of saying that, maybe you'd just like to say, what was the percentage chance that I fell out there? People understand percentages a little better. So that's what the p-value is. So instead of saying -2 compared to -1.96, let's just calculate the probability of being out there in that little tail with the z-stat of -2, and let's state that. And so it's the smallest value of alpha for which you can reject it. All right. So let's see. How would we do that? So yeah, right. If the p-value were less than the alpha, then we should reject it, right? if alpha over 2 is out here, and we get alpha over 4, we should have rejected it. Or we could calculate, you know, the p-value for both sides and double it, you know, however you want to look at it. If p-value is greater than alpha, yeah, do not reject. Well, that's because that means you were in here. The probability was high that you got that. So let's see. If you can't remember that too, because some people get backwards, they think, I want a big p-value. That means that means I should reject it. You know, well, no. You know, you want the little p-value because it meant the probability was very low that you got the test statistics that you got. And so they got this little thing to help you remember it. If the p-value is low, then H0 must go. It's not bad. Yeah, it's not bad. I use it because again, you'll forget and you'll run some ANOVA and you'll get a p. You're like, oh, did I want a big one or a little one? You know, I want a little one to get rid of it. So the 5-step process, I don't know why they put a new process. It's the same. It's the same, right? State your hypotheses, choose your alpha. You know, is it a z-test or a t-test? That's all that's saying. So we can use the same words next time. Collect the data and compute the z-stat or the t-stat, and then make your decision. Instead of this time comparing two critical values, well, this time just compare your probability you got to alpha over 2. So it's the same approach, just looking at the box from the other side. You know, it's still a square. You know, it's just you're looking at the white side or the black side. That's all. Okay, so here they're gonna do this for you too. Yeah, so they're gonna go through the same problem, right? So look, nothing's changed. We've got the 30 millimeter bolt. We got the same standard deviation, the same two hypotheses. Okay, we picked the same alpha and the same n, so nothing's different. We haven't done it's a darn thing. 1 and 2 is the same as it was before. Number 3, same as it was before. This is a z-test because we know the standard deviation. Oh, look, we took the same sample. That's good. So we got the same mean, the same n, and so now let's get the z-stat. We got the same z-stat. We haven't done a darn thing different. Nothing. All right, so now here's where the difference comes. So now instead of comparing 2 or minus 2 to 1.96, let's just go use our dist function, plug in 2 and see what probability we get. All right, we plug in 2, we got 2.28% in the green. You plug in minus 2 and you got 2.28 out here. So the total rejection area was twice that, right? Both of them added up, 4.56. That's less than 5%. Oh, okay, get rid of it. Because it was a 4.56% chance that we got this statistic, this X bar equal 29.84 or worse. We could, there's some worse ones we could have gotten, right? 27, 24, 38. Okay, so there's a 4.6. In fact, I think they state that. Nah, they don't state it that way. The book does. There's a 4.5% chance that you could actually get that statistically worse, but that's pretty low. That's lower than your 5% that you were willing to draw the line at. And so, okay, well, let's get rid of H0. P was low, so H0 had to go. So P is less than alpha, so you reject it. So state the conclusion again. There's sufficient evidence that concludes the average diameter is not equal to 30. So the P and the critical value, same thing. Just how are you going to express this conclusion? With the comparative critical value or comparative percentage. And you can see how that has value. Let's see.
I know that's a low
Yeah.
chance, but what would you do?
I think in my mind, if it wasn't costly, I'd just do another one just because it's weird. But as I recall, I think you could keep it, but you're risking yourself, yeah, because it's close. So then again, you have to ask yourself, well, how costly is it for me to make that mistake? Yeah. But I think we're stating that if it's less than it, drop it. So I think if it's equal, you could do it. But you'll read things where they say when it's close, it should bother you. Like when we get into design experiments, when we look at the ANOVA, that's one of the comments they make. They say, well, don't get so excited. It was, you had 5% and it came out to be 5.1. Well, don't get so excited like that. Maybe you do have some correlation. That's so close that, I wouldn't. I'd be suspect or worried about it. So let's see. Now, could we have used confidence intervals? Yeah, It's the same, right? We could have gone in here, taken that same old sample with our same standard deviation, our little ON, got our confidence interval around this guy, and look, there's our 95% confidence interval around that sample mean of 29.84. And look, it does not include the 30 that we thought it did. So that's the same interpretation. Oops, it's it goofed up. That sample, if we put a 95% confidence interval around that sample, it doesn't capture 30. Therefore, that sample probably did not come from a population that had a mean of 30. Okay, it's not telling you that, right? It's saying that in most probably 95% probability the diameter is between here and here from if that sample is truly sampled from some population. And so the conclusion is the same. So you got three ways to look at this. Whichever way you think expresses it clearest to the people you're talking to, or do them all three, right? Because they're not any harder. I mean, right? This is the same sample. That's the same standard deviation. That's the same test critical value. That's the same n. It only took 2 seconds to calculate the other direction. Maybe you express it that way. It doesn't fall on a confidence interval. My critical value is less than or my test statistic is less than my critical value, or my probability is lower than alpha. Say it all three ways. You really hit it home then, and it's the same amount of math. All right, and then just like last chapter, do we ever really know the standard deviation? Most of the time, no. So, well, when we don't know it, hey, guess what? You can do a pilot sample and estimate it, or hey, we can go to the t-test, right? And is that any harder? No, everything's the same, right? And maybe instead of z.dist, you put t.dist, right? And oh yeah, we forgot there was one other parameter. That was the degrees of freedom. That's it. But very very small, so no difference to see. So use the t distribution instead of the z distribution. Yeah, and the t distribution, yeah, you assume that you're coming from a normal population, and so you might have to check it, right? You might have to, if you're worried that your population is not normal, maybe you need to do one of those normal probability plots, or look at a histogram or something, or just take a sample that's big enough where you're hoping things are okay. So let's see. So here we're on the other side, right? Sigma's unknown. Do the t-test, and oh what? Well, we got a t-stat, right? And remember, it's just this with s in there, the sample standard deviation instead of the known standard deviation. That's why they're using s. And of course, then we compare it to critical values from the t distribution, or we're going to compare our p-values to probabilities from the t distribution. Either one. So let's do an example, since it's going to be the same procedure. So let's see, the average cost of a hotel room in New York is $168 a night. Unless you stay at Trump Towers, right? Whatever one of his hotels, right? And from random sample of 25, we got 172 and a half. This is our mean. It's a sample statistic, not a parameter. S, remember, sample standard deviation, 15.4. So at the 5% level, our alpha is 5%, is this true? Here's our hypothesis, right? Our null hypothesis is we think that the average cost is $168. So our alternative is no, it's not. It's equal, so it's a two-tailed test. We're going to put 2.5% in the one side, 2.5 in the other, and we're going to get our critical values and compare it, or we're going to do our p-value, or we're going to do them all. Let's see. I forget what they do. So yeah, here's our picture. We're putting 2.5% in each side. We're going to throw it away if it's out here, if our statistic falls out here. N is 25, so remember our degrees of freedom was 1 minus the number of samples. Remember that came from the, that heuristic discussions. If you had the mean and you had all the numbers known but 1, you could calculate that other. So you only had degrees of freedom of 1 minus the total number of points you had. So our standard deviation is not known, so this is a t test or t statistic. So we go to our t table with 24 degrees of freedom and 0.025, and we come up with that. 24 degrees of freedom, 0.025, that's the same. And remember, I thought I'd pull this up just so because I don't know that I've shown this. I think we showed it one time, but remember, here it is. I think I got it here. Right. So let's see. We have 24 degrees of freedom, and we're putting 5% up there. Yeah, it's not fast to do that, is it? Okay, there. How's that? It's doing it. Let's see. So we had 24 degrees of freedom, right? And we wanted 0.025. So there's the number. 24 degrees of freedom. We're putting 0.025 up in the top. 0.02639. I hope that was the number that was in there. Was it?
Yes.
Otherwise, I don't know what I'm doing, and which is not, it's not impossible. I could, right? Let's see. I think it's how you do this, isn't it? Or is that, am I going to be in trouble if I do that? I can't remember now what it was set up at. Okay, so I won't do that. I won't do that switch next time. All right, let's see. There. That's a good sign. Yeah. No, yeah, it's 0.02639. Yay! And it goes both ways. Remember, it's symmetrical, right? And did I have to go to that table? No. Remember, we got Excel to do it for us. Just put that in there, and I'll show you how to do that too. So our t statistic, that's our measurement. There's our projected mean. Here was our standard deviation from our sample. So it's 1.46. Okay, we're in there. We're in here. Yep, we're happy. So do not reject it. There's insufficient evidence to think that the true mean cost is different from 168, even though we had a mean of 172.5. That's still there. So statistically, we've got a way to state this. Now we're 95% confident. Yeah, because we had alpha as 5. That our conclusion is correct. So let's see. There's Excel doing it for us. Yeah. So they're using T inverse and T dist. And I'll also show you there's some new ones too. There's some T dist 2T. They got T dot dist. And when we get, so we don't switch back and forth, I've got them all in one Excel file for you, and we'll look at how we can get the numbers in the table out of Excel. And do I always remember how to do it? No, I always forget every time I go back to it. So what do? I open the book to the table, and I pick one number that I like because it looks pretty and it's in the middle and it's easy for me to see or something. And I try the Excel formulas twice. I try the distribution to make sure it gives me the number in the table, and I try the inverse, make sure it gives me the probability. And then I say, okay, I know how I'm using this. And why do I do that? Because Excel has T dist, it has T dot dist, it has T dot dist dot 2T, it has T dot dist dot RT for right tail. It's got a bunch of them. And I want to make sure I'm using the right one. And so it's more important that you know what you're trying to get, right? I'm trying to get this critical value, and it needs to be this, because I can look in the table and see what it is, or because I can open my book and look at one example that they worked, and then go to Excel, make sure you got the right function, then you can put it in yours. This is what I always do. Why does Excel have this one and a bunch of new ones? Because remember, when they move to new versions of Excel, they think it's better to name it one way or another, but they're backwards compatible. So T dot dist will work, or T dist will work, or they want to be all encompassing, of course. So just be careful is all I say. Run an example that and so you're using it right. Let's see. Okay, so now they're going to do the same conclusion with a confidence interval, right? Boom, here's your mean, there was your critical value, there's your standard deviation, there's your N, and so, if we do the confidence intervals, right, this confidence interval contained the hypothesized mean of 168, so we don't reject it. It's close to the edge over here, but that's okay. It's still in there. Remember our discussion a few chapters ago, how they had all those confidence intervals, that several of them, and when they said, when you are 95% confidence, that means that 95 out of 100 confidence intervals would probably contain it, but 5 of them wouldn't. Well, this one did. It was good. So we don't have any evidence to reject the null hypothesis. So now we're down to this other little idea that instead of looking on both sides, let's just look on one side. Why? Well, because, we've got a one-sided hypothesis, right? So let's see, in many cases, the alternative hypothesis focuses on one direction. So here, we think we have a process that has a mean that's greater than or equal to 3. So that's our null hypothesis. So our alternative hypothesis is, well, it's not. It's less than 3. So now we only care about the means that come on this side, right? Because we don't care about the big ones. There's no rejection up here. Even if we take a sample and it falls up here, we're not rejecting. We thought it might be bigger, right? That's what we said. We think our hypothesis says it's bigger. So it's okay to fall up there. So in this case, on a greater than or equal to case, this little land up here is okay. This is your reject down here. Now, if we had a less than or equal to case, then we flip-flop, right? We're okay down here on the low side, and we don't like the high side. And so now all we got to do is make our conclusion just looking at one side, which means we just look at one critical value, right? We look at the plus one, or we look at the minus one. That's all. Or we look at one part of the P. Yeah, so there's only one critical value since the rejection area is only 1/10. Right? We were happy with bigger. We're throwing away the little one. So our critical value, the only one we care about, is the minus one, if it's a Z, the minus one, or the T. But again, notice the subtlety that they threw in there. If it's my view graphs, I'd have made it giant red or something. It's alpha, right? Remember, we've always, in our two-tail, we've had Z alpha over 2 or T of alpha over 2. So again, what I'm saying, if I'm going to claim 5% and I'm a one-tail test, I'm throwing all 5% down here. They did draw it here, right? Because that's the only thing that makes sense, right? If I'm talking about my percentage of times that I want to reject, and if it's two-tail, I got to put the total percent in both half. When I'm going to talk about a percentage rejection on a one-tail, well, I have to put it all down there. So that's the only thing that you'll notice that's different. All your 5% goes in there, your 10% goes in there, whatever it is. So let's see. Oh yeah, see what are they doing? They flip-flopped, right? So now this is the less than or equal to case. So we're happy down here. We're not happy up here because we flip-flopped our null hypothesis.